set 1 through 16. That's not due till this Sunday, but if there's any questions from that, we can take some questions from 1 through 16 here to start. If not, that's okay. I suspect that not a lot of us did much during vacation, which you shouldn't have. You enjoy your vacation. No. Okay, very good. So we're going to start here in section 15.2. So in section 15.1, we talked about exponential functions and logistic functions. In section 15.2, basically, we're going to see some applications of those things. So we'll start by defining the exponential population model. We'll use this almost exclusively in this chapter, or this section, I should say. So the exponential population model is P of t equals P naught times 1 plus r over 100 to the t. So P of t would represent the population at some time t. P naught would be our initial population. R is the rate of change as a decimal, or I'm sorry, as a percentage, excuse me. And then T is our time, really in the same unit as the rate of change. So whatever that time unit is, really we're going to be expressing, you need to express time consistent, or that unit consistently. Okay. So last time in section 15.1, we had talked about exponential functions that look like this, a times b to the x, where b is positive and not equal to 1. Remember that there were two types of exponential functions. There is growth and decay. By looking at my f of x equals a times b to the x, how can I tell whether that's a growth or decay function? Let's say assuming that the a value is positive. Well, b has to be positive and greater than 1 for it to be an exponential function. Yeah, so decay, b is between 0 and 1, and growth, b is greater than 1. So notice that our population model is still an exponential model here, right? Where our 1 plus r over 100 is really the same thing as our b. And our P naught is really the same thing as A. Everybody's okay with that? Since we're talking about a population, initial population always has to be positive, right? You can't have a negative population. That makes no sense. Everybody agree? So what I can do then is I can just look for if that 1 plus r over 100 is greater than 1, it's growth, and if it's less than 1, or it's less than 1, it's decay. Everybody's cool with that idea? Let's do a example here. just to get used to using this formula and thinking about this still as a exponential function. So it says here the directions indicate whether the following population models are growth or decay. And then the second part would be to find that constant rate of growth or decay. So if I'm looking at part A, how can I tell by looking at this equation whether this is growth or decay? What do I have to look at? I just have to look at the value of B, right? So in this case, for part A, is this growth or decay? Growth. How can I tell? Because it's greater than 1. And then if I'm doing the same thing for part B, this one is decay, because it's between 0 and 1. Very easy, just using some definitions, right? No big deal. The second part of the question asks for the constant rate of growth or decay. That's basically just asking for the value for R. Everybody's okay with that? So above, we observe that 1 plus R over 100 is the same thing as our value for B. So to solve A, I'm just going to take 1 plus R over 100, set it equal to my value for B, and then solve for R. So I'll subtract 1 from both sides and then multiply by 100. And I get R is 3.84%. That feel good to you guys? For part B, I can do the same thing. Here, when I subtract 1 and divide by 100, I get that R is negative 1.33%. Do you observe a relationship between whether this is growth or decay and the value for R? Yeah, if R is positive, it's growth. If R is negative, it's decay. That makes pretty good sense, right? If the rate of growth is negative, it should be getting smaller, decaying. If the rate of growth is positive, it should be growing. It's, getting bigger. Okay. Let's do another example. So here we have, it says, determine the population model with an initial value of 15, increasing at a constant rate of 6% every year. Well, it says to use a population model. So I know I'm going to be using P of t equals P naught times 1 plus R over 100 to the t. And since it's a model, I know that I'm going to have a dependent and independent variable inside of my equation. So I'm not going to be plugging anything in for P of t or t. What will I be plugging in for P naught? 15. That's the initial amount. And plugging in for R will be 6, because that's the rate of change as a percentage. And if I wanted to simplify this down, 1 plus 6 over 100 is 1.06. And then we should probably say what unit t is in. We'll write t in years so that it matches the unit on R, right? Pretty easy, right? Very straightforward there. Let's look at another example. So I read this: determine the population model with an initial value of 15, increasing at a constant rate of 6% every 6 months. The only thing that's different from this example to the previous one is instead of happening every year, it's happening every 6 months. So that piece is always going to be, that part, much of it's always going to be the same, right? Now, it's reasonable to write this model where t is in with two different kinds of units for t. What 2 units for t would be plausible here? Or reasonable to use? Years and months, right? Happening every 6 months, maybe we want to write t in years or t in months. So let's do it once with years, and then we'll do it again in months. Bless you. Now, I can't just write to the t here because the units aren't matching up correctly, right? Because the rate of change happens every 6 months. So my question for you would be, okay, if we're writing this function where t is in years, how many rates of change do I have inside of 1 year? 2. Why? 1 rate of change happens every 6 months. There's 12 months in a year. So instead of writing t in this spot, I'm going to write 2t. I feel okay there? Okay. So let's think about what would happen if we wanted to write this model with t in months. So how much of a rate of change is complete inside of 1 month? Lily? 1/6. So instead of writing, because it takes 6 months to do 1 rate of change, after 1 month we've done 1/6 of a rate of change. So instead of writing t, we're going to write t over 6 or 1/6 t, either is fine. So depending on the directions of the question, one or both of these answers might be appropriate. This question doesn't indicate how to write that model, whether they want a t in years or months. So either answer would be fine. You wouldn't need to give both. If the directions for the question ask for t in years or t in months, then one of them would be correct and the other would be incorrect. But the way this is currently worded, either would be appropriate. Is everybody cool? Again, not a big deal. All right, next example. Again, if we're doing anything and you're not sure what I've done, or you have questions, or you just need me to slow down or repeat something, holler at me or whatever. Sometimes I get excited and start really rocking. Okay, so our next example says, suppose that a colony of 120 bacteria is put into a petri dish, and that culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. When I read this, I really read 2 separate kind of steps or parts of this question. This part that I've highlighted in yellow sounds like write a model for this situation. And then this part in green sounds like, okay, then use that model to solve for one specific scenario or one specific situation. Everybody cool with that? Now, I think from the context of this question, the model I should be using would be the population model. How can I assume that from the problem's context? It's talking about an organism reproducing, right? It's like textbook population in the way we think about population, right? Should be super obvious. Is everybody clear on that? Again, a lot of the difficulty here in this section just comes from like reading and decoding things, so I don't want to take any of that kind of stuff for granted, as the math pieces of this have been pretty simple. It's just mostly like, can you read a paragraph or a couple of sentences and decode it into symbols? Okay, so we're writing a population model. So what is my value for P naught? $120, yeah. Just shout it out if you know it. If I didn't hear it, that's okay. And then we need our value for R. What's our value for R going to be? Now, it doesn't say it explicitly, right? What word in here is going to be telling us our value for R, though? Lily? Doubles. So the word doubles implies what percent change? What? 100% is correct. If that wasn't obvious to you, this is the way you want to think about this. So let's say you had 2 things, and then you had 4 things. Okay? What percent of 2 did you have to add to 2 to get to 4? 100% of it, right? So double means 100% change. Okay, with that? Now, what unit should we write t in? What unit of time? Hours seems appropriate. Now, this doubling happens every 3 hours, so instead of t, I need to write t over 3, right? We get 1/3 of a double in an hour, because it takes 3 hours to do a full double. And if we simplify that down a little further, 1 plus 100 over 100 is 2. Boy, that looks a lot like doubling now, right? So that's, oops. So there's like our yellow piece. Now for the green part, the question asks how long. So what are we going to be solving for in a question that asks how long? Yeah, we're going to be looking for t, right? So to solve for t, we're going to have to be plugging in for p of t. What are we plugging in for p of t? A population, in this case 400,000. And then, how did we solve problems like this before we left for break? Does anybody remember? Lily? We didn't break out a logarithm yet. That will be what we will use here shortly. But we just graphed this on our calculator and found the intersection. I'm going to continue doing it that way until we've properly introduced logarithms, but certainly it would not be incorrect to use one here. I want to be clear. All right. So all I do to graph or to solve this is I'm going to graph the left-hand side. Yep. And then the right-hand side. And then before I graph this, I'm going to have to reset my window. This is doubling every 3 hours. So at 3 hours, there's 240. 6 hours, there'd be 480. 9 hours would be 960. It feels like it's going to take a long time to get to 400,000. I'll go 0 to 100. So I figure by 100 hours, I'll probably be there. The Y's are going to be representing the populations. So the minimum population would be 120. I'm going to just round that down to 0 because it's a round number. The maximum population I care about is this 400,000, but I'm going to use 500,000 just so that my line that I'm solving for isn't just at the very tippy top of my viewing window. It's a little bit easier to see. And we'll go up by, say, 100,000s. So there's my 400,000 line. Here's my population curve. There's my intersection. To find that intersection, we press second and the trace button. Choose the intersect command. And then since there's only 2 curves and 1 intersection, I can just press enter 3 times. And my solution is at 35.11 hours. Everybody feel okay doing that? As an aside here, if you are, scheduled to take an ACT or something like that here relatively soon, this method of solving by graphing is an effective one, especially if you don't know algebraically how to solve something. You can always graph both sides and find the intersection or intersections, and that's a perfectly reasonable way of solving something, particularly if ew, what is he? I'm not sure what to do with that. Just FYI. Another situation where we can apply a logistic or exponential model to solve is radioactive decay. And I think you guys talk about radioactive decay a little bit in your chemistry class. A really, really simple definition of this would be you have some substance, and that substance gives off subatomic particles, and in the act of doing that, turns into a new substance. Does that sound relatively familiar? Okay. The rate in which that substance gives off those particles to become a new substance is called the half-life. So it's the amount of time it takes for half of the original substance to turn into that new substance. For us, though, what we really care about is what half-life means in terms of R. So what percent value does half-life imply R should be? If you go to a store and something is half off, it's 50%, right? But keep in mind, what type of situation is this? Decay. So what should R be? Negative 50%. Yeah. The nice part is whenever we're in a radioactive decay situation, we can assume, and we're given information about a half-life, immediately we know that the R is negative 50%. Everybody's cool with that? Now, I can still use my population model for this because it's essentially we have atoms of original substance decaying into atoms of a new substance, right? It's still it's like a population, right? Because we're talking about a finite things. So let's look at an example here of doing a half-life problem using our population model. So it says, suppose the half-life of a certain radioactive substance is 35 days, and you have 10 grams of the substance initially. Find the time it would take for there to be only 1 gram remaining. Again, when I read this, it reads to me like 2 separate questions. The first question would be like, write a model given this information. And the second question would be, solve that model for this specific scenario. Everybody kind of cool with that? Again, we just mentioned why it's still appropriate to use our population model for a radioactive decay situation. What's my value for P naught going to be here? $10, right? I heard somebody whispering it. You guys are so quiet today. And our value for R should be -50. And that half-life is happening every 35 days. So what unit should we use for T? So T would be in days, and then I'll use T over 35. Seems the most appropriate. If I simplify that down here, that would just 1 plus -50 over 100 is just 0.5. Boy, that looks like half now, huh? That's pretty nice. And then we're interested in how, or find the time. So again, solving for T. It would take for only 1 gram of remaining, or 1 gram remaining. So my P of T should be 10. So, calculator time again. So, left-hand side, right-hand side, and then we'll reset our window here. Think about this situation. So after 35 days, we're down to 5 grams. 70 days would be 2.5. 105 days would be 1.25. And then like 140 days would be like 0.625. So I'll go 0 to 150. I know that that half-life is happening somewhere between 105 and 140 days is when I'm crossing that 1 gram boundary, but that ought to do it for me. The minimum amount of substance I'll ever have is 0, because all you can do is decay down to nothing left. And then the Y max would be the, since it's decay, whatever you started with would be the maximum you could ever have. Everybody's cool with that? And then we'll go up by 1s. So hit graph, here's my 1 gram line, here's my decay function. There's the intersection I'm looking for, right around a little bit after 100. Second trace, intersect command, enter 3 times. And I get 116.27 is my value for T. So everybody feel okay doing these radioactive decay problems? They're all kind of the same, right? Is this any really different than the previous problems? No, man, it's the same thing, right? The only tricky part was remembering that half-life means R is -50. Woo! One of the other things we talked about in section 15.1 was that realistically, an exponential model is not always really the best model to use when describing a population, because a lot of times populations can't get infinitely large, like you can get with an exponential model. So another model that we can use that's often effective is a logistic model. So the logistic model is nice because you have like two asymptotes built into it. So you have an upper bound and a lower bound, where it kind of looks like that in between. The lower bound here happens at y equals 0, and the upper bound happens at y equals c. Oops, I think kx, is that what it was? Let me think here for a minute. No, I think it's just to the x. Yeah. Oh, I guess let's write it in the same format it's here. Where our x, or our logistic model, is c over 1 plus a times e to the negative kx. So this is the just kind of like recapping what we talked about with logistics from last time. So our problem says you start a bunny petting zoo, aren't you, the little entrepreneur? Really putting the manure in entrepreneur there. Because you're running a zoo, you're going to have to be picking up animal poop. That's what manure is. Have I beaten this joke into the ground yet? Yeah, okay, good. You determine that the population of bunnies on your farm can be modeled by the equation b of t equals yada, 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 where t is measured in years. Part A asks, how many bunnies do you have initially? Part B, what is the maximum sustainable population for bunnies on your farm? And C, how long will it take for you to have 500 bunnies? Let's just knock these out one at a time, just right in a row. So how many bunnies do you have initially? What value of t does initially imply? 0 is correct. You were starting to say it. Yeah, so initially it would be before anything happens. That would be at time 0. So all we're going to do is do b of 0. So negative 0.5 times 0 is 0. E to the 0 is 1. 99 times 1 is 99. 1 plus 99 is 100. 800 over 100 is 8 bunnies. Or you could type that into your calculator if you wanted to. I preferred the mental math because it worked easy this time. Cool with that? Part B asks for the maximum sustainable population. Really, that's just the upper bound. So in this case, we know the upper bound is y equals c. The c in our case is 800, so we just have 800 bunnies. I didn't do any math there. I just used some definitions about what I knew about logistics. Alternatively, if you had forgotten that the upper bound is at y equals c, if you had typed that function into your calculator and graphed it and just looked at what was happening as the x-axis got very big, you'd see the y value is like capped at about 800, and it wouldn't take too much for you to probably guess that 800 would be that maximum sustainable population. Part C says, how long? Oh, what are we doing there? Solving for t. Will it take for you to have 500 bunnies? So that 500 is a population. I'll plug that into b of t. Oops. And then we'll solve this. Again, we'll use our calculator to do this the same way we had done before. So left-hand side, right-hand side. To type in that right-hand side, I'm sure as heck going to use that fraction option. So alpha y equals, and then choose option 1. Because I don't want to muck around with having to get all the parentheses right on my calculator if I don't really have to. Oh, Boise. What happened there? Okay. Now they got that all typed in. Let's reset our window. I don't know, 0 to 100 is probably enough time. Bunnies have a reputation for reproducing quickly. I think there's a off-color idiom talking about how fast bunnies like to reproduce or how much bunnies like to reproduce. You guys can think about that on your own and smile on when you think of it. For the population, I know the lower bound for the population is always going to be 0 for logistic, and the upper bound is going to be C. So 0 to 800 feels pretty good there. I'll go up by 100s. And let's hit graph. There's my 500 bunny line. Whoa! There's my population curve. That happened pretty quick. Second calc, or second trace, intersect command, enter, enter, enter. So it took about 10.21 years. I hope you had a big business expansion plan, because you went from 8 bunnies to 500 bunnies in 10 years. It's a lot of manure. Any questions about these things that we've done so far here today? This was, again, very similar to the things that you would have done in section 15.1. So if you hadn't done that homework yet, really we're using the same solving techniques to deal with the story problems you would have done in 15.1. You just wouldn't have had to like write your own model. They would have given it to you in the problem or whatever. So it's should be pretty good there for most of those problems. 15.3 we'll start now. Now, as Lily pointed out earlier, all of these problems that we've been solving by graphing, yeah, of course. All of these problems we've been solving by graphing, really we could solve using a logarithm. So let's get to it here. We've danced around the existence of a logarithm for long enough, I think. So that's what we're going to do today, is we're going to define a logarithm and talk a little bit about the properties, and probably next time we'll get into the solving piece. I don't think we will not get there today. So our definition for a logarithm says, okay, let's say we have some exponential equation, right? And I know for an exponential equation, the b value has to be positive and not equal to 1. But let's say a little bit more about this. So if I have some positive number and I raise it to a power, what kind of answer am I guaranteed to get with that? Positive number raised to a power. Has to be positive. Might not be bigger, right? If you had something like 1/2 squared, that gets smaller, but it will stay positive. So we know in this case that y is also positive. Okay with that? Our standard definition for a logarithm says that I can rewrite this exponential equation as a logarithmic equation. And because these two equations are equivalent, everything that we knew about the exponential equation goes with us to form or is also true for the logarithmic equation. The piece that's really important for us with regard to logarithms is the piece that b has to be positive. What that's saying is that you can't take the logarithm of a number that's not positive. So log of 0, undefined. Log of a negative, undefined. That becomes quite important when we start using logarithms to solve things. So I want to make sure I highlight that now. Everybody's cool so far, though? All right, so what is this logarithm really saying? Well, it's the answer, or it's the answer to an exponential equation, right? So if I asked what power of b gives me y, that power of b is log base b of y. Or in other words, if I ask, say, like, what power of 2 is equal to 3? Well, that power of 2 is log base 2 of 3. That's just the name we give to that number. Oops. Now that number has like a decimal representation also. If I wanted to fire up my calculator, I could type this into my calculator. To type in a log of any base like this, I'm going to press the math button, scroll down to the bottom till I find the log base command. And then I can just type it in just like it looks like on my sheet of paper. So log base 2 of 3 is 1.58, yada, yada, yada. Probably an irrational number. Everybody's cool with what I mean by a logarithm here? Hopefully this rings some bells. Again, we did this a year ago, but it was a year ago, so. And also tends to be not a very sticky subject. This tends to be something that, like, when you do it in Algebra 2, everyone's like, what was the thing you remember the least from Algebra 2? Logs. It's fine. That's why we're doing it again. Let's just practice with this definition a little bit. So we're going to just evaluate some logarithms by hand. So we'll do some examples here. So let's say I want to do log base 4 of 16. Okay. So I'd start by saying, okay, let's let that equal x. So I have a logarithmic equation. Then I can use my definition of a logarithm to rewrite this as an exponential equation. Right? So the base of the logarithm is the base of the exponential. The argument of the logarithm is the solution to the exponential. And the solution to the logarithm is the exponent in the exponential. But this should be pretty easy. 4 to what power is equal to 16? 2. Right? 4 squared is 16. Easy mental math problem. Still doing good? Okay, let's keep going. Log base 5 of square root 5 is, set that equal to x. Do the same thing. So I have 5 to the x equals square root of 5. And what's the square root is the same as? Lily? 1/2 power? Yeah, absolutely. So that just tells me x is 1/2. Right? The property that Lily used down there was that the nth root of x equals x to the 1 over n. If you didn't remember that right away, I'm going to write it down so you can, make note of that for later as it comes up. Again, that was something we would have talked about last year that ideally you remember, but if you didn't, that's why we're reviewing, right? Half the point of doing these examples is to review exponent properties. So let's say we have log base 3 of 1 over 27. Again, we'll rewrite this as a exponential equation. What's the exponential equation that I'd write here? Very good. 3 to the x equals 1 over 27. So not so clear how I'm going to rewrite 1 over 27 as a power of 3, but 27 is 3 to the third, so that can be 1 over 3 to the third. And here's the tricky piece. I have this property for negative exponents, right? That x to the negative n is 1 over x to the n. I'm going to use that here and rewrite that as 3 to the negative 3. So if I make the reciprocal and make the exponent negative, that's the same as doing nothing at all, because the negative exponent just makes the reciprocal back, and you're back where you're undoing what you did. So x is just negative 3. So what if we have log base 12 of 1? Again, we'll write that as an exponential equation. So I have 12 to the x is equal to 1. What's x have to be? 0, right? We know that any non-zero number to the 0 power is equal to 1. What's 0 to the 0? It's undefined. It's actually indeterminate is the technical term for that situation, because depending on how you look at that problem, you could have x, it would equal what, 1 or 0, or there's a couple of different things that, like, depending on how you're thinking about it, would look, and that's not the world we want to live in mathematics. You don't want indeterminate mathematics where, like, oh, sometimes 2 plus 2 is 4, but some other times when I feel like it's going to be 7, you know, like, what a nightmare. So we're just going to call it undefined. If you take calculus next year, we'll talk about some of the indeterminate forms as it comes up in that class. So if you're signed up for that, get ready. Log base 8 of 8 is equal to x. We write that as an exponential. So I have 8 to the x is equal to 8. What's x? Yeah, it's 1, no dir. So I have basically 4 observations that we can make based on these examples. So we have the couple of, we'll start with the 2 easy, or the 2 most obvious ones. So if I take the log of any base, or log of any base of 1, that should equal 0, right? Because b to the 0 has to be 1. I know that it can't be undefined because the b is the base of an exponential, so it has to be non-zero. So we can't ever run into anything weird going on there. How about log base b of b? What's that have to equal? 1, right? Because b to the first is equal to b. If we recast that as an exponential. Okay. How about log base b of b to the y? What does that have to equal? Has to be y. Notice that this is just a special case of the more general case of the previous 3. If I try to recast this as an exponential equation, I just get b to the y is equal to b to the y, which, golly gee, that better be true, or else we've just broken math here. Or you're living in a brave new world where things don't have to equal themselves. Yikes. Yikes. And then my last observation is, oops, that's what I mean, is b to the log base b of x. What does that have to equal? Just x. Why is that the case? Well, notice this is an exponential equation that I've written. Right? So I can rewrite that as a logarithmic equation. So it would be log base b of the answer should equal the exponent. Well, log base b of x better as heck equal log base b of x. Going forward, these last 2 are the really critical ones, particularly when we get into solving. As the first one is showing us that we can cancel an exponent base by using a logarithm. And the second one is showing us that we can cancel a logarithm by using an exponent base. So it's going to allow us to solve exponential and logarithmic equations, those final two observations. I'm just pointing that out now because we're going to circle back to that in another lesson or so. Cool? Okay. So there are two special kinds of logarithms. The first one is called the common logarithm. The common logarithm is log base 10, but we don't write it as log base 10 because why would we? We're going to write it as log with no subscript written at all. And we're going to understand that that means log base 10, which is not uncommon, right? When we write a square root symbol, we don't write the index of 2 in there. We just know that it's index 2. Because we've decided that when we don't write an index, it's index 2. Same idea here. If we don't write a subscript on a log, we know it's just log 10. Why is that going to be important to remember? Because if you're solving a logarithmic equation, you have to do the exponent base to both sides. You need the exponent base that matches the logarithm, so you have to remember log is log 10. The other special one is the natural logarithm. That's log base e. Again, we don't write it as log base e. We write it as ln. Notice when I'm writing my logs here, I'm always writing them as script, like as a cursive. I'm doing that intentionally because I've seen over the years students frequently will, if they get confused in a problem, will turn a log into a 10g and then start doing all kinds of weird things like dividing by 10 and solving for g, and you'd be surprised how strange things can happen. But I'm going to specifically try to write everything in cursive. I'd encourage you to do the same thing if you think that's a possibility of something that you might do. I want to point out to you that your calculator has built-in buttons specifically for the common log and the natural log. So if I wanted to do the common log of 1,000, well, that's actually a mental math problem. What's the common log of 1,000? A 1,000 is 10 to the third, right? So log base 10 of 10 to the third is 3. Or if you wanted to do, say, the natural log of 7, is that one a mental math problem? No, because there's not an obvious way to rewrite 7 as a number with base e. That's just going to be some hairy-looking decimal. Everybody's okay? All right. Next up. So we have 4 properties of logarithms that we need to talk about. So the first one is called the product property. And this says that log base b of xy is equal to log base b of x plus log base b of y. And now this looks a little odd, right? Notice that multiplication inside the logarithm is turning into an addition outside the logarithm. And you might say, boy, that seems strange, Mr. Kulik. And I would say, not so much. We've seen this kind of happen before. If you think back to exponentials, if I multiply 2 exponentials with the same base, we add the exponents. You're seeing that multiplication outside the exponential turns into addition inside the exponential. Essentially, this product property is just the logarithmic version of this exponent property. And that shouldn't be surprising considering that a logarithmic equation is just a translation of the exponential equation, right? Oops. Next up is the quotient property. Oops, forgot my T. So here we have log base b of x over y equals log base b of x minus log base b of y. So division inside the logarithm turns into subtraction outside the logarithm. Again, we've seen this before with exponents. So if we think about the quotient property of exponents, division outside of the exponential turns into subtraction inside the exponential. Same idea, just the logarithmic version of that property. Next up is the power property. This says log base b of x to the c is equal to c times log base b of x. So you're seeing that an exponent inside the logarithm turns into multiplying a coefficient outside the logarithm. This property is the logarithmic version of the exponent of an exponent property. So you're seeing the exponent outside the exponential turns into multiplication inside the exponential. Now these three properties that we've done so far, the three that you'll most commonly use. Okay, we'll use these to do solving. We'll use these to do some other kinds of problems here. The fourth property is one that you will almost never use, but was like the most critically important one when Mr. Kulik was a student. What has changed between now and then? Calculator technology is the answer. So I'll explain to you a minute how Mr. Kulik had to use this property and why it was so important to him and why it's not important to you anymore. So the change of base formula says that log base b of a is equal to log base c of a divided by log base c of b. The important thing here is that this base c is a base of your choice. So when Mr. Kulik was a student, if he wanted to do log base 2 of 3, he would write this as common log of 3 over common log of 2. And in Mr. Kulik's math classroom, we used a 4-function calculator. So what we did is we turned to the back of the textbook to our table of logarithms, looked up the value for log of 3 and log of 2, and then typed that into our calculator as that number divided by that number, pressed enter. By the time I was like a senior in high school, everyone had a scientific calculator that probably had log or natural log built into it as a button. But we still had to do this. We still had to rewrite it as log of 3 divided by log of 2. Why doesn't that matter to you? Because your calculator, you can go math, log base, and just do log base 2 of 3 and do it directly. You don't need to use the change of base formula because your calculator can handle it. So in one short, I guess it hasn't been that short. It's been some years, but calculator technology has changed the importance of that piece. All right, let's prove one of these properties. and then we'll be done. So we're going to start by proving, or we're going to finish, I should say, we're not starting anything, we're ending the class by proving the product property. So I'm going to start by defining capital A as log base B of x and capital B as log base B of y. Now I can use the definition of a logarithm to rewrite these logarithmic equations as exponential equations. Everybody's okay with that? I'm going to take these two exponential equations and now multiply them together. So I'll multiply the left-hand sides together and then multiply the right-hand sides together. B to the A times B to the B becomes B to the A plus B. Everybody's cool? This is now an exponential equation. So I can again use the definition of a logarithm to rewrite this as a logarithmic equation. And what is A equal to? That was log base B of x. And what was B equal to? Log base B of y. And that's exactly what I wanted, because that is now the product property. I think in the homework we ask you to prove some of these other properties. The proofs for the other properties can be done similarly. Start by writing a logarithmic equation, translate those logarithmic equations into exponential equations, manipulate the exponential equations using the equivalent property of exponents, as I pointed out in the notes, and then transform them back using the definition of a logarithm again, and I think should be able to sort those out. If not, I'm sure that somebody will ask about them when we have a chance to talk about homeworks. We'll stop here. This felt like enough. That was a lot of stuff that we just burnt through. At this point, you guys can do up to 70 in the homework set. I know. But some of these problems are literally like type this into your calculator problems, or like evaluate this logarithm problem. They weren't time consuming. But that's where we're going to stop. Okie doke.